equations. The first one is Schrödinger's equation. The second one is Einstein field equation, quantum mechanics and general relativity. And of course, it is not exactly the general case, but my discussion is philosophical, and equations are only auxiliary. And they are the core, including the philosophical core, about theories. And now about the problem of consistency about theories, one of the deepest problems in the contemporary physics. And it is my viewpoint to the philosophical essence of that problem. Both include different viewpoints to motion, to mechanical and to motion in a philosophical sense. Quantum mechanics represents this as a leap, as a jump, as a revolution. And it is as an evolution in general relativity. And now about the axiom of choice, which is the most important viewpoint to both to be reconciled in a mathematical viewpoint. And it is the way a curved trajectory to be represented as a series of leaps, as quantum mechanics requires. And about the underlying mathematical structure, both. It is, of course, only a suggestion, a conjecture. The philosophical sense of the structure is to unify smooth and curved motion and discrete but straight leap. And it is a kind of unification of standard and non-standard interpretation, for example, in the sense of Robinson's analysis. And now about the physical sense. It means a smooth continuum to be represented as a series of leaps. For example, discrete leaps, for example, quantum leaps. And the basis is quantum information, the conception of quantum information and its units, quantum bits, qubits. And now it is connected, linked to the mathematical sense of time. Time in physical theories is two types, two kinds, reversal and irreversible. And the deepest sense is both kinds of time to be reconciled to each other. And the sense of information is maybe to be both kinds of time, reversible and irreversible, to be reconciled to each other. And now, cinematographic metaphor borrowed from Bergson. We have a kind of representation of smooth time, of smooth motion, as a series of frames. It is borrowed from Bergson and his creative evolution, 1907, I think. And it is possible the axiom of choice to be used for the same purpose, because the axiom of choice is able to represent a smooth motion as a series of frames, as in Bergson's metaphor. And one can see the axiom of choice in the place of the camera in Bergson's metaphor, which makes different frames. And so the physical sense of the axiom of choice is to represent smooth motion is that series of frames. And any frame is physically equivalent to a single measurement. So we have a representation of the coherent state as a statistical ensemble, which means that two kinds of probabilities are equated to each other. And it is very close link to the problem of hidden variables in quantum mechanics. We have two theorems, Neumann 1932 and the fundamental Cohen-Specker 1968, that those excludes any hidden variables in quantum mechanics. It is impossible to have quantum hidden variables if the formalism of the separable complex Hilbert space is relevant to quantum mechanics. And we have the shot of a quantum leap by the kinematographic metaphor. That shot is a very fuzzy and comprise all space. It is a kind of metaphor for the wave function. Of course, the wave function of coordinates, but it is a metaphor for all kinds of wave function, if we have the appropriate space. And the quantum states before and after measurement, they should be equated to each other, because our knowledge should be right, should be true. And now about from the mathematical to physical equivalence. We have the problem of mathematical equivalence of both equations, Schrödinger equation and Einstein field equation, and the problem of the ontology behind that equivalence. My presentation refers to the ontology, because here is a philosophical conference, of course, and this is the address of the talk. This is the deep ontological essence if both equations can be mathematically equated to each other. And this is on the base of quantum information, and the concept of choice is the track to that ontology. And now my thesis. The thesis, the whole of both universe and a quantum, can be equated in a sense. And we have some arguments and that viewpoint. Of course, it is very, very strange because universe is very, very big and quantum is very, very small. And we have a kind of ontology which may be linked, for example, to that of Nicholas of Cusa, or some kind of cyclic ontology as that of Nietzsche, for example. So we have all the universe, all the big universe, according to my thesis, within a single quantum. Of course, the out of the universe is absolutely unknown, just as the externality of one quantum, one single quantum. And it is possible both to be equated to each other in a mathematical sense, but the essence of my talk is the ontology behind that mathematical considerations. Of course, possible objections might be both are too different in scale. Of course, it is the biggest, the universe, and it is the smallest, a quantum. And of course, it is very paradoxical. Another possible objections, too different in mass and energy. But mass and energy are not enough, because the essence of quantum mechanics is action, the quantity of action, and it is possible things very different in mass and energy anyway to be equated in action. And of course we have many, many quanta within universe. So we have some very, very strange transition from inside to outside, after which one becomes many, many, many. Of course, it is not impossible from a mathematical viewpoint, but it is interesting to be argumented by philosophical reasons. And another objection, the problem about the Big Bang, because we have a Big Bang within a quantum. It seems very strange. It is absolutely impossible at first glance, but we have some ways to be reconciled both viewpoints, the expanding universe and the statics of a quantum. So I have many, many arguments. You may read them in internet if you type the title of my presentation. It is in YouTube and in many other places, so we may have it in detail if you want. So I thank for your attention and please for your question.
Thank you very much. It's perfect in time, so we have more time for questions and discussion.
Probably I have some question just for understanding. When you mentioned this, what's outside is what is inside is also outside. If we try to understand the universe as a single atom, as a single quantum, it little bit surprised me because you know, we can say something definite about the quantum only after measurement. And if the universe is an atom, is a quantum, then no measurement are possible. Then we can say nothing about this quantum, neither of its size, neither of its mass, nor of its energy. In fact, in my opinion, the quanta couldn't exist without quantum field. So the basic concept is quantum field rather than quantum itself. And when talking about this general problem of the consistent theory, which could include both the theory of relativity and quantum theory, in my opinion, the most important problem in it is the problem of horizons, even horizons.
Of what, excuse me?
Horizons. For example, black hole horizon,
Thank you.
all that, because the descriptions of reality before and beyond any horizon couldn't be complementary and inconsistent in this way. Well, in fact, I understand now that something very important in your talk missed my. I missed to appreciate it. I missed something very important in the understanding of your thesis.
Yes. The first point, I think that quantum should be postulated as the same in the case of measurement. Of course, it will be a theoretical postulate, only postulating what is quantum, when the universe is a quantum. We have to postulate that universe is a quantum. So we have no measurement here. This is the first point. The third point about horizon, yes, I think that the problem of universe as a quantum is the same problem of horizon in a philosophical sense, because we have the universe as the horizon inside and the same horizon outside as a quantum. So it is a new viewpoint to the problem of horizon, but not in terms of black holes, but in the more fundamental for the theories notions. And excuse me, what was your second point?
About quantum field.
Yes, quantum field. So, according to me, quantum field should be represented as a space in each point of which have a wave function. Is it right?
Not completely, yes, but let's accept this.
Okay, let's accept this. So, we have the problem how to represent space and space-time by concepts by means of wave function. I think that pseudo-Riemannian space and Hilbert space, exactly separable complex Hilbert space, can be isomorphic to each other. We have a representation which is a Minkowski space which is curved. This is the pseudo-Riemannian space. Yes, it's right, I think. Okay, may I think it is here. No. Yes. But it is very slow. Please. So we have pseudo. It is Minkowski space. Minkowski space. Yes, it is good to be for Minkowski space.
Okay, with light cone.
Okay, and if we curve it, we will obtain pseudo-Riemannian space. Do you understand me?
Yes.
Yes, okay. And now, it is possible this space to be represented as Hilbert space if we make
Sorry, I didn't. Which space?
Hilbert space.
Hilbert.
Hilbert.
Okay.
Here have to substitute time with frequency. It is a Fourier transformation. It is not very difficult to be made, and we this is a series of qubits. For example, E and so on. Those are the axes of Hilbert spaces, and any axe corresponds to a state in time.
So this is for wave function representation.
Yes, yes. So we have to represent Hilbert space and this quantum field as a gravitational field. This is the core. It is possible to make a direct way for transformation from the quantum field to gravitational field in the sense of the transformation of Hilbert space to pseudo-Riemannian space. But it is very roughly, of course. Very rough.
Okay, so, other questions? Okay, thank you very much.
Thank you.